one of these things will work. Okay, so the more progress you have, the more better feedback I can give you, and probably the better your projects will ultimately be. Okay, so it says also, yeah, so what progress have you made? What some of the basic approaches you've tried? You know, these are good things to do. Maybe some thought of what you think you might try to do to improve beyond the basic approaches that you've already tried. Let's say your project at heart is a clustering project, and you've gotten kind of some version of k-means clustering working, but you want to try some other types of clustering formulations, or you want to change the underlying metric from Euclidean to something else. These are ideas of how you can move beyond, and I can give you feedback on which I think are most appropriate or which are most likely going to show the most interesting results. And then kind of what experiments you're going to do or are going to attempt to do to show the effectiveness of this. One thing is often clear to students at this point is, okay, I've got my data, I've run something, right? Here are the output of the results. For the final reports, I'll want you to somehow try and evaluate how well it worked. Okay, now this how well it worked is pretty vague. It could be kind of in some sort of, you kind of show the significance of your result in some statistical way. This is one approach. It could be that you just want to show the runtime that this approach is significantly faster than this other approach. Sometimes it's harder to do either of these, and you really just want to kind of give some empirical picture. And I can give you hints that, okay, there's not a good quantitative way to kind of evaluate between these, but what you can do is you can bring out certain examples to kind of, as kind of a qualitative or at least anecdotal demonstration that that stuff seems to be working. And I'll try and give you advice on these things. Now, if you have some initial ideas, then that's great. I can tell you which ones of these will be good, and I'll try and propose my own. Okay, so don't worry if you don't know how well it's working yet, but for the final report, that's something that you'll want to be keeping in mind. Okay, so if you have, I hope everyone has seen the sign-up sheet posted on Canvas. If you have trouble figuring out how to sign up, or there aren't any times at work, send an email to the. Please send an email to Madia, the TA, and he can help sort these things out. But there should be enough spots for each of the groups. Okay, any questions on the intermediate report? So, okay, so there's not too much, specific you absolutely have to do at this point. You'll be getting feedback from me and from your peers starting Wednesday. Okay, also note the regression homework was posted on at the beginning of break, so you can start working on that as well. So great. Okay. Let's see. Okay. So we're going to talk about the singular value decompositions and its relatives, mainly for applications in different types of dimensionality reduction. Okay, and so what this means depends on your input in various ways. And so there's this metric learning lecture where I've split off a bunch of the other variants of this, and that'll either come on Wednesday or more likely actually next week we'll go into more detail. So what the goal here, hold on, my pen's not working, I need to sync it. Hopefully this. So just give me a second, otherwise I won't be able to write on the slides, and you'll have to try and see the chalk, which will not be good. Okay. Good? okay, so so good. So we're going to start with some input. Let me tone this down. Okay, input A, which is going to be a an n by d matrix. Okay, so we're going to think of this as A. We're just going to have n columns or n rows and so d columns. And so I mean, you can view this as either n data points, each is d-dimensional, or d data points, each n-dimensional. In this case, we'll think about each row is going to act like a data point. So that means it's in RD. It's going to have these d different coordinates. It's not. Okay, great. So each data point, each AI is going to have these d different coordinates. Okay, and so the goal of this topic is going to basically be to find a so the goal is to find a subspace, and I'll call this F, and so this will be a k-dimensional subspace, and so k is going to be much less than d, so that all the data lies very close to this subspace F. Okay, so it's hard to draw a picture, and I'm in very, very high dimensions here, but think there's some very high dimensional subspace, and that there's some low dimensional subspace F, right? So I've only drawn one dimension here, but I want all the red points to be close onto this black subspace, and I want them to be close in the orthogonal direction now. Right, so I'm going to measure the residuals differently than I did in linear regression. One way is that F is not full dimensional. That's one difference. The other is that I project directly onto the subspace. So I'm looking at the distance to the closest point onto the subspace. Okay, and so if I have a data point here x, then this data point here, this one that projected onto the subspace, I'll label this projection of x onto F. Okay, and I'll explain this notation using linear algebraic notation soon. Okay, but this is the main operation. I want to kind of look at this projection to the closest point. Right, so I'll say that so this is going to be the arg min of some point P on the subspace F of closest between P and X. Okay, so I'm minimizing this distance. Everything is going to be in L2, right? So I'm just looking at the straight line distance here, right? So this is arg min, and so then ultimately my goal is going to be to find F star, which is going to be arg min of F, where this is the rank of F equals K, and the origin is inside of F. That minimizes the sum over all of the rows of A. Each row of A is a data point in d dimensions. The difference between X and the projection onto F of X squared. Okay, so this is ultimately going to be my goal. Okay, so this is just the first overview slide of this section. I have data in this high dimensional space, right? Each of these guys is going to be an AI, and this is in RD, right? So the d-dimensional space. I want to find this F, this low dimensional subspace. This is going to be only k dimensions. So think of, if k is 2, that means I can project it to 2 dimensions, and then I can draw a picture of that, right? Or it might be 10 dimensions for other reasons we'll talk about. And so I want to look at the residual of the mapping x to the closest point, that's pi of f, right? And so then I want to, and the f I want to find, f star, is going to be the one that minimizes the sum of these squared, these squared residuals. And for now, we'll talk about that the origin must be contained in f. And we'll take away this assumption kind of later on in this lecture. Okay, we'll see why this makes it convenient if you haven't seen it before. Okay. So is it kind of the big picture clear, right? So I want to find a lower dimensional subspace that basically captures the data as well as possible. So we'll see a different formulation of dimensional reduction later, maybe on Wednesday, where we're going to try and kind of make sure all the distances have to be close to their original, every point is somehow close to that structure pairwise. Every pair of points, the distance is close to the original pair after I've done the reduction. Here I'm taking an average, so some of the distances, some of these terms might be very large, but on average the sum of the squared terms is small. Okay. All right, so let's just quickly review some linear algebra. Let's say if f is equal to ui, so now where ui is a unit vector, okay? So if ui is going to be a unit vector, right? So I can view it as a point, and that means I can take its norm, ui is equal to 1. The norm of this is 1, and it's a vector, which means it contains an origin. So this is a valid thing. If it's and this is the case where k equals 1, then the projection onto ui of some x turns out to be exactly the dot product ui of x. Actually, I can multiply times ui. Okay, so how does this look? I can think of extending this vector here, and then if I have actual data point ai, the dot product gives me this value, this length. The distance from the origin times dotted with ui gives me some value right there, and if I multiply this by ui, so it's going to be on some negative value, maybe this is going to be negative 0.3, and then if I look at this point right here, this would be projection of ui of x is going to be this actual data point right here. I'm multiplying this ui vector by a minus 0.3, so I go backwards through the origin. And this one vector gives me a one-dimensional subspace, and I get this projection just by doing the dot product. Okay, so this dot product is this really powerful operation which is doing projections for me. Basically, the dot product only gives me the length, but I can multiply it by the direction of this vector. Okay? So then if I want to do this for a full subspace, for f, I can describe some f via some basis. I'll call this uf, which is going to be u1, u2, up to uk, such that each ui is going to be a unit vector, just like this one, and I'm also going to have that ui, uj, the dot product is going to be 0 for I not equal to j. This means that they're going to be force them to be these unit vectors are going to be orthogonal to each other, and this tells me that this is a k-dimensional basis. That's what a basis is. Hopefully you remember that from linear algebra. Okay, so if I have this representation of f, this basically tells me the span of these vectors tells me this subspace f. And this is how I'm going to represent f. And so that means that for any point, I can write for any point p in this subspace F, then I can write P as the sum over I equals 1 to K of AI, of alpha I ui, where alpha I is going to be this dot product ui p. Okay, so if p was originally has d coordinates, each of the unit vectors has d coordinates, right? That's how I write them in d-dimensional space. But I can take the dot product with each of these unit vectors and I get a value, and then I can write this by, and each of these unit vectors has d dimensions, but I can decompose each p which lives on F. So if I have a point that lives on the subspace, I can write it in terms of these coefficients and these unit vectors. Okay? Effectively, this gives me a new coordinate system to talk about P. So I can talk about P in, say, this basis as some k-dimensional point, alpha 2, alpha k. Right? So this is effectively this is a point in Rk now. This is now k-dimensional space. I can write it by just these coordinates I found with this dot product. Okay, so if I have another direction here, this is u2, this was u1, right? And so I have a point, let's say A, I have a point A here, I extend u2 here, and I project onto here as well, I'm going to get a value negative 1.3, then the coordinate of AI, this is AI, not alpha I, in UF is going to be minus 0.3 minus 1.3, right? So I now have a two-dimensional coordinate. Maybe originally there's a bunch of other dimensions that are coming out of the board that you can't see here, but the two dimensions U1 and U2 live on this board, and I can project it onto these two-dimensional subspace, and I get these two coordinate systems now. Now it's not the x and the y coordinate system. That's fine. We'll see a little bit about rotations in the plane a little bit later. But it gives me a two-dimensional coordinate system, which allows me to describe this as just in a lower dimensional subspace, and I can now draw pictures of it if it's in 2 dimensions. And I can do this with every data point AI, and I get a smaller coordinate system. Okay, hopefully this is all review from linear algebra. Otherwise, or from the foundations class. Otherwise, this is probably coming pretty quickly. Okay. All right. Okay, so how do we find this F star, right? So how do we find this F star which is going to minimize this loss function right here? Right? It seems like I can now explain it. I can start talking about these projection operators. I kind of have an understanding of how to represent this F star, but how do I calculate it? We're not going to actually talk about how the algorithms actually work in class, but I'm just going to tell you, you're going to call this operation, call this singular value decomposition. Okay? Who's not heard the singular value decomposition before? Okay. So this part will probably go pretty fast for you guys. But hopefully all the mathematics you need is in the notes, and there's great Wikipedia articles and linear algebra textbooks on this. But here's a very fast introduction to this if you haven't seen this before. Okay, so we're going to start with this n by d matrix. Oh, there's one more thing I forgot to say about that's really important for these matrices, these matrix A. This must be this has to be a data matrix. I want every coordinate to basically have the same units. every chord should have the same units. It could be like I'm measuring the price of the stock on D consecutive days. I'm measuring the temperature at D different weather stations at a single point in time. Right? So each point in time is D measurements of a weather station. Right? I'm looking at all of the kind of a room full of people. I'm looking at how much income did you write on your tax returns last year. Right? So they're all in the same units. The reason is because I'm now measuring the residual in terms of kind of an L2 distance, which is kind of treating all these units as equal. So with regression, I could kind of avoid this a little bit, although if you regularized it, you have the same sort of issues. But here I'm taking these L2 distances, so whenever you see this, you should think they should really have all the same units. So if I have height and weight as the different coordinates and age as different coordinates here, be very wary, because if you change, if I measure age in years or in days, it's going to completely change the meaning of the output of this. Okay, you'll see a lot of examples online where they use different coordinates objects as the examples, and those don't really make sense. Okay, so just keep that in mind. That's an important point. Otherwise, you'll start doing some weird stuff that's not going to make sense. Okay. Okay, so back to this singular value decomposition. So I've got my data matrix here, and what this is going to do is it's going to decompose it into 3 matrices, right? And these matrices are, in general, bigger than this one, which seems to say, okay, this is going to make computation harder and so forth, but these will capture a lot of information in them. Okay, so to kind of get a sense of what's going on here, this matrix, S matrix, is going to be all zeros down here, and off the diagonal is also all zeros, and so on the diagonal value here, it's going to have these values. This is going to be an n by n matrix and a d by d matrix. It turns out that most of this matrix is completely unimportant. Because this is all zeros down here, basically everything over here is multiplied by 0 in this product. So it doesn't really matter what I put in here. Okay? It turns out that we're going to have the rows of this are going to all the rows of this are going to be unit vectors, and they're all going to be orthogonal. Both U and V are going to be orthogonal matrices. So all columns are U and V. So this is V transpose. Okay, so the columns of U and the rows of V transpose are going to be orthogonal vectors, and there are going to be unit vectors orthogonal with the other columns or rows. Okay, and we'll see what these mean shortly. And these aren't going to matter so much, other than they're going to be orthogonal with the first set. The first D are going to be worth computing usually, but the ones, the n minus d ones over here, are not interesting because these are all zeros. Okay. Okay. So here's some annotation. Let me do it on here. Some annotation of what's going on here. Think of this as, this is AI. This is one. This is one data point. A column in here is going to be UI. This is going to be a left singular. So a left singular vector, and corresponding the right the row of V transpose. So the column of V. This is going to be a right singular vector. And associated with each of these is going to be a single scalar value here, SI. This is going to be the ith singular value. And what's nice about these SIs is this is going to be S1, and I'll have S1 is going to be greater or equal than S2, greater or equal than S3, SD, and these are all going to be greater or equal than 0. If A is not full rank, then I'm only going to, and it's only rank R, I'm only going to have R of these which are non-zero. Then the bottom D minus R are going to be all 0. And these are going to be in order, and so they're going to tell me how important what's going on is. So the first singular value corresponds with the first left singular vector, and the top with the first right singular vector. And the value of it tells me how important it is. So the more important ones are the ones with the lower indices. Okay, and we'll try and capture what the importance is here. Okay, and so one way I like to think about this is you can kind of draw this picture of this ellipse. And basically, if I look at the matrix A and I multiply it by a vector x, okay, and x starts out as a unit vector, I'm going to get some vector it starts out as a d-dimensional vector, it's going to end up as an n-dimensional vector, and this is going to lie on some sort of ellipse. Okay, and what the ellipse is going to say is going to correspond to is the singular vectors of this decomposition. Actually, let's walk through an example of how this works. Okay? So let's start with this simple matrix. This is 4 data points here. So 4, 3, the first data point here is going to be 4, 3 here, right? So x value is 4, y value is 3. Okay, and there are 4 data points up here. I've chosen all of these so that the average of them is the origin. Okay, otherwise this is gonna, some stuff will end up working kind of weird, and we'll come back to this point. Okay, but if I average all the x coordinates, if I add up everything in the first x coordinate, it's going to be 0. Same with the y coordinates. Okay? And then I can take the SVD, and it's going to look like this. I get a square matrix here for U. This S matrix is n by d again, but it's all zeros down here, and the off-diagonal terms are zeros. And this is a d by d, a 2 by 2 square matrix again. And if I look at these, the row here, this should be it should be a unit vector. So if I square those terms and add them up, they should add to 1. Same with the columns here. Okay. So what happens now if I take a data point x? Okay, we're going to look at this data point where the x value in this picture, the x value is basically 0.24. And the y value is 0.97, right? So that's this point x here. And I'm going to kind of step through what happens when I multiply by ax. So I'm going to look at ax, which is going to be equal to u v transpose x, right? So a is equivalent to u times s times v transpose. So if I multiply x by a on the left, it's going to be the same as if I multiply by u times s times v transpose on the left, which means that I can first write down what is the result of v transpose x. Then I can look at what is the result of s v transpose x. These are all valid operations I can do. And then I can look at this, s u v transpose x, which is equal to this result. But I can kind of step through these and see what each of these matrices are doing. Okay? And what is this first matrix doing? Well, it's telling me a new basis here. So this is going to be V1, and this is going to be V2. These are these are both going to be so unit vectors which are orthogonal to each other. And I've drawn them on this picture here. So let's look at V1. x coordinate is negative 0.8, the y coordinate is negative 0.5. It's going to be right here. This is the unit vector for v1. Okay? The unit vector for v2 looks over here. They're orthogonal. Right? These vectors are orthogonal with each other. That's a right angle. Okay? So now what happens when I multiply x, the vector x, times this matrix V? Well, I can just multiply by each of these, take dot product. The multiplication is just a dot product with each of these vectors. Right? So I take the dot product of x with v1, and what value am I going to get? Well, I can take v1 and extend it out through here and project x onto here, and I get this length here, and this is about, I'm going to guess this is like negative 0.7. Okay? And I can do the same thing with v2 here, and this is going to be about positive 0.6. That's my guess there. Right? And then I can draw that on this picture. So what I've done is now I've drawn v1 on the x-axis, v2 on the y-axis, and I can write this coordinate down. Right? So the v1 coordinate, this is negative 0.7, and the y coordinate, which is the v2 coordinate, is positive 0.6. Right? So maybe I have it off a little bit here, but right, so this is what I've done. The first, an orthogonal vector, v transpose, when I multiply it times the transpose of an orthogonal vector, I'm doing a change of basis. That's what's happening here. I'm only in 2 dimensions, so I can draw the original coordinates of x are based on these x and y coordinates, or these x1 and x2 coordinates, and I'm giving a new coordinate system based on the new orthogonal vectors v1 and v2. Okay, and so I can draw this picture now. I can now make the x-axis v1 and the y-axis v2, and I can draw this picture, and x becomes xc, right? So this xc, this weird Greek symbol I chose for some odd reason, is now the result of v transpose x, and it has 2 coordinates itself. I multiply a 2-dimensional vector by a 2x2 matrix, so I get back a 2-dimensional vector. It's exactly these coordinates here, and I can think of it in this coordinate system. Okay? So the first, the right singular vector matrix is just a change of basis. That's what it's doing. Okay? The next step is to multiply by this S matrix, which was this this rectangular thing, but it only had values on the diagonal. A diagonal matrix is just a scaling matrix. I'm scaling, but I scale each coordinate now. But I'm not scaling the original x coordinates, I'm scaling the v1, v2 coordinates. Right, so the value of s was, I didn't write this down here, if we go back, 8.1 and 2.3. So I go back here and I'm stretching out this by 8.1 and this one by 2.3. Right, so I've taken an original unit ball here and I've made it this, like this Mahalanobis ball. Remember if we remember the Mahalanobis distance we talked about, that's what I'm doing here. I'm skewing the distance, the Euclidean distance. The ball becomes this ellipse instead, and I'm exactly stretching it by these factors. 8.1 is the first singular value, so I stretch the v1 coordinate by 8.1 and the v2 coordinate by 2.3. Okay, and so that's eta is now the result of doing this. So I've taken this 6c and I multiply it by s, and I get this eta value here instead. Still a two-dimensional value or two-dimensional vector, but it's been stretched out in this way. Okay, so the point of what was going on here is that I wanted to stretch out the data, the multiply x, I wanted to stretch it out by a certain way, not the original xy or x coordinate system, the original coordinate system, but by a different one. So I need to first change the basis, and then I can use the diagonal to stretch it out. Okay? This makes sense? And so, if you remember, this S matrix actually had two other rows that I haven't used yet. It's actually stretching not just by the V1 and V2, but these two other rows. This is needed to get the dimensions in the matrix multiplication to actually to line up. And so think of there are two other coordinates which are coming out of the board here, but they have a stretch factor of 0. So it's an ellipse, but it's restricted to be super skinny in these two dimensions now. Okay, and because the matrix A was at most n by d, the rank was at most d, so I only stretch it in 2 dimensions. Right, that was d dimensions. The other ones are fixed at 0 stretch. Okay, and then this U matrix, the last one that came in the end, it basically rotates it back to apply to the individual columns of A, and that essentially is another change of basis, but now in this 4-dimensional space. So I've taken this 2-dimensional ellipse of values, and I've rotated it in the 4-dimensional space. Kind of like the first step here did a rotation, but now it's happening in 4 dimensions, and I can't draw a nice picture anymore. Okay. So when I think of this matrix A, so this is kind of a procedural definition of what the SVD does, is that it allows me to turn A into this part where I'm changing the basis, and then I'm scaling along this new basis directions, and then I'm undoing this, or I'm translating it back onto the data points. But if I think of that as A is actually capturing data, then it's saying that the data is actually lying in this rotated 2-dimensional kind of ellipse. And this is capturing where most of the data is lying in. Right? So the data is going to end up in the d-dimensional space. This ellipse will be directed along the directions that have lots of data in them. And so that's inherently what's going on here. If there's a lot of data in, so if I have these data points which lie kind of like this, and for now, if we happen to have the origin goes through the center here, then what's going to happen is V1 is going to be in this direction, and then V2, right, is going to be out here. But notice there's more data times V1, so that means that, say, sigma 1, or sometimes you use sigma instead of S1, so S1 might be something like 3 times S2, because there's 3 times as much data variance along the V1 direction than there is the V2 direction. But what's interesting is the V1 direction is capturing the direction with the most variance along the data. Okay. All right, so what I want to explain now is that what the SVD is capturing is going to be the best rank K approximation of the input A. All right, so I assume if you've seen the SVD before, you've kind of seen this kind of relation between SVD and this. Let's just go through this. And this is essentially going to be solving this F star problem, the optimal subspace problem. And so if we go back to, but what I'm going to show is that the SVD this decomposition of the matrix A into these components, you're going to essentially be able to read off this basis which defines F from this SVD, right? From the singular vectors of the SVD. So what a better definition of what V1, this is the top right singular vector of A. What I can view this is as the R max of all the unit vectors in RD, which maximizes AU. And you can square it, it's easier to think of it the square, right? So it's the single direction which maximizes when I multiply this by A, it's maximizing this norm. This is equal to okay, so it's maximizing the sum of the squared dot products with AI, with all of the data points in AI, right? So V1 is the first singular vector, right? Singular vector. V1, it's maximizing the sum of the dot products, right? So when I project a data point onto this V1 subspace, I get the length along there, and I want the direction which maximizes all of these squared lengths. That's what the top singular vector is defined. And then there's a way to define the next top singular vector as consider all the ones which are orthogonal to this, find the one that maximizes this, forcing it to be orthogonal with all the ones that come before it. Okay, so that would be a typical way of one way how to construct this SVD. All right, so and so it turns out that that S1 squared, or in general SI squared, is going to be equal to this value, VI squared, right? So if I look at this term is actually A times the ith right singular vector, this norm squared is SI squared. Right, so this is going to be sum of AI in A, let's say Vj. Right, so the sum of these dot products, the squared dot products with Vj is going to equal to this, to the squared singular value. And I can also write that the Frobenius norm of A, which is sum AI and AI squared, right? So if I take the sum of the square of all the individual elements of A, or the sum of the two norms squared of the vectors, that's equal to what's called the Frobenius norm of A. It turns out that this is equal to sum over j equals 1 to d of a vj squared, which is equal to sum j equals 1 to d of sj squared, right? So the Frobenius norm, which is kind of a generalization of the two norm to matrices, is this the sum of all the squared singular values. Okay, so effectively what this means is that if I think of this recursive construction of the singular vectors this way, where I find the one that maximizes this, and then I factor it out, and I find the one that maximizes what's left, it actually means that the VD, the last singular vector, is the one that minimizes this. So the D singular vector is the one that minimizes this. Okay, so that means SJD is, SD squared is the smallest possible direction. And so that means that if I want to find the set of directions which minimize the sum of these residual distances, then I want to kind of find essentially the bottom D minus K dimensional subspace, and those tell me the sum of those directions. Right? So, another page here. So it means that F star R min of F rank F equals K, or right, so this is going to be equivalent to, because this is a projection operator, is going to be equal to R max F rank F equals K of some actually I want to do arg min of right, so I want to maximize this, or I can say equals to so I can define something called F star perpendicular, which is going to be RD set minus F. So this will be a D minus K dimensional subspace, and then I can basically equivalently define F star this way as the arg min of F rank F is equal to D minus K as okay, so I can say if I want to find the space, the subspace, the D minus K dimensional subspace that is minimizing the sum of the projections onto it, then this is going to be equivalent, right? So if I'm here, if V1 is F, then what's orthogonal to it, V2, is F perp, the perpendicular to it. So I can find the subspace which minimizes it, okay? And so if I know that what's minimizing are the smallest singular vectors, then I can just pull these out. It means that F must correspond with the top K singular vectors, and F perp must correspond with the bottom D minus K of these singular vectors. Okay, because I know the projection onto the subspace F perp is going to correspond with this cost function that I have, this residual cost function. Okay, which means that all of this kind of implies that I can define F by the span of U1, U2 up to UK, and I can set Uj into Vj, where this is the jth right, so singular vector. Okay, so the top K singular vectors describe the basis of the optimal rank K subspace, or K-dimensional subspace that I want to project all my data onto. Okay, and so the singular value decomposition, there's a whole bunch of nuance in the right way to calculate it. There are simple ways like the power method, which is described in the textbook, but there are other situations where you want to do other things. This is a really old problem that's been studied extensively by numerical linear algebra researchers, and there's this library in Fortran, this library in Fortran that's called LAPACK, Linear Algebra Package, that is used by linked to by all major programming languages. It's the default thing to use in C, it's Fortran, so you can call it directly if you want to. In MATLAB, it's what's used. In Python, it's what's used as the default. Right? So everything calculates a singular value decomposition basically the same way in the backend. If you take a numerical linear algebra class or a scientific computing class, you can learn much more about how to compute this in interesting ways. But we're just going to use this as a black box. Okay? And in the homework, you'll use, I think it's set up for MATLAB, but it's probably not much hard to do in Python. Okay? The biggest difference between MATLAB and Python is that in MATLAB, the matrices look like this, where S is n by d. In Python, this is d by d. Actually, they store as a d by d matrix, unless you set some flags in some weird way. So then if you try and recover V transpose times S times U, it does not, the operations aren't valid. But in MATLAB, that works. And Octave is a free alternative to MATLAB you can use. Okay. Okay, so what is the best rank K approximation doing by picture? Before we said all of this stuff before was all zeros, right? So all of this did matter. Basically, what the rank K approximation is doing is saying I only care about the top K singular vectors and values, so I can basically set these singular values to 0. Effectively, it means this part of the matrix is 0, and this part of UK is also uninteresting, and now this part of VK is uninteresting, and I have V1, V2 up to VK, which are left here, U1 up to UK, which are left here. And if I multiply this part back together again with the S1 up to SK, this part, I'm going to get this matrix A sub K. Okay? This matrix A sub K is going to have a rank K. I can think of A sub K as being equal to the sum equals J equals 1 up to K of U, J, S, J, Vj transpose. This is going to be, this is just a scalar. This is going to be an outer product between n-dimensional and a d-dimensional matrix. So this term is going to be an n by d matrix. And I'm adding k of these together. But this is a rank 1 n by d matrix. When I put k of them, they're going to be rank k. Okay? So this is going to be a rank k n by d matrix. And so it's going to be the rank K matrix such that right, so this is going to be, it's going to minimize, so over all rank K matrices AK, this is going to minimize the Frobenius norm. It's also going to be the arg min of rank. Sorry, when I have slides, I can write B where the rank of B is equal to K of A minus B. It's also true for the 2 norm of these matrices. So now I can write this in matrix form, where I write matrix differences. I have to have the same dimension on the matrices in order to take a difference between them. Okay, but if I calculate the Frobenius norm or the 2 norm here, the optimum is going to be this A sub K, which is constructed this way. Okay, this gives me this kind of includes, this forces all the data to lie in some low-dimensional subspace, but it still writes it with the d-dimensional coordinates. If I just want the k-dimensional coordinates, what should I do? Okay, so to see who's paying attention, okay, so now that I've gone through this all very quickly, if I just want the k-dimensional coordinates of the data after I've done this, that is basically the k-dimensional coordinates on the low-dimensional subspace. How do I get those for the data points? Okay, so each data point needs to have k coordinates, and how many data points are there? N. There are n data points, right? So I need to do something with n, and I need to get k coordinates out. This value from each of the data points, right? So in here, the x-axis, the average value is here. If I subtract this from every data point, it shifts the whole thing over to here. So it's centered on the x-coordinate. I do the same separately for the y-coordinate. I can do these individually, right? And then I run the SVD. And then I take the same way as before. Okay, so the difference between, and this nomenclature, if you look on the web, sometimes people will say the SVD is doing principal component analysis, but I think this is in some places, not just in my notes, but I like to use these two names to differentiate between them, where principal component analysis is making sure it centers the data first, where SVD is just this matrix operation. Okay? So it's sometimes very important to do this, especially if I want to get, say, a one-dimensional picture of this data projected down to one dimension. I'm going to do much, much better with PCA than I do with just using the SVD. Okay? Okay, and then one more thing I want to cover in this lecture, eigenvalues and eigenvectors. So who's not heard of eigenvalues and eigenvectors before? So just one or two of you. Okay, so I think we mentioned them in class with respect to spectral clustering. So if you haven't seen this before, it turns out they're very related to the singular vectors. So these, I start with a square matrix B, and let's say that this is going to be an R d by d. And so, and it if I write b v equals lambda v, if I can find a vector, so this is a square matrix, so if I'm multiplying something by this v is going to be a d-dimensional vector, and it's the same one over here. So this would be an eigenvector, and then this is a scalar, and this is an eigenvalue. Okay, so if I have a square matrix, then I can find vectors that satisfy this. So if I multiply b times a vector, I get back a scaled version of that vector. Then this is an eigenvector of b. Okay, it turns out if b is full rank, then they're going to be exactly d eigenvectors, and they're all going to be orthogonal to each other. Okay? What does that kind of sound like? Kind of sounds like the singular vectors. Okay? And so this they're basically the same thing through some if I start with a if you remember the singular vectors, I start with an A matrix which is n by d, and what I can do is I can create a BR matrix, which is going to be A transpose A. Right? If I do this, this is now going to be in D by D. I can alternatively do a BL, which is going to be A transpose. This is going to be in R n times n. It's going to be an n by n matrix here. Okay? So it turns out the singular vectors, the right singular vectors of A are going to be the eigenvectors of BR, and the left singular vectors of A are going to be the eigenvectors of BL. Okay? And the singular values squared are going to be the eigenvalues. Okay, so how to see this is that I can write BR times V, right? Remember, A is going to be U S V transpose. So if I write BR times V, I want to show that these right singular vectors are going to be eigenvalues, right? So that looks like the correct left-hand side of this eigenvector equation here. I need to show that this corresponds with a scalar times this vector, this set of vectors again. And so I can expand this now. A transpose A times V. And now I can do the SVD expansion of A. VSU transpose. So if I take A transpose of this, you kind of reverse the order and you transpose every term. S transpose is itself. And this is U, S, V transpose, V. What happens here is that these two terms, orthogonal matrix by itself becomes just the identity matrix. Same thing happens here. There might be some projection going on there you have to be careful about, but what happens when you get left is V times S, we'll call that S squared. Remember, S was this diagonal matrix, so when I square it, I just square all the terms on this diagonal. And look what I got back. I got back a scaled version of the original vectors, right? So this BR matrix times V, I get back the same vectors, which that means they're eigenvectors, scaled version. They're not scaled by the singular values, but by the squared singular values. So the eigenvalues are the squared singular values. Right, so, okay, and so I can do this with the left. I can do a similar sort of expansion around BL and show that the left singular vectors are the eigenvectors of SL. Some of the eigenvalues, if n is bigger than d, this is not full rank, so that some of the eigenvalues are going to have to be 0. And so that's why on some inner term here, if I put the V here, let's just maybe go through this quickly. BRU is going to be A transpose U equals US V transpose VS U transpose times U. So this part here cancels, that's fine, but this V transpose V, these are actually a smaller rank, so I'm actually doing a projection here. So I can't really get rid of them, but it turns out this S matrix kind of takes care of that, in that when I do this, I have a bunch of zeros on this diagonal. So I can effectively cancel them, and which means I'm going to recover back U times S squared again. So I'm going to get this same effect here, right? So the singular values and eigenvector decomposition are closely linked in this thing. So if you can calculate one, you can calculate the other. If you can say something about one, it essentially tells you something about the subspace it captures in the others. Okay, so your intermediate reports are due on Wednesday. Remember, they're due at noon. Bring printed out versions to class and sign up to meet with me. And then probably Wednesday we'll talk about random projections, which will be a different way of doing dimensional reduction. And then we'll talk about some other ways to use the SVD to do other forms of dimensional reduction next week, and we'll do some streaming versions of this stuff as well.